This is a sample problem
We're going to talk about the Texas sample calculation.
The
Opstar's video for section 4
Power
as the drawing shows, the support cable
Now,
runs through
one thing that
the boom
people get confused about is the difference between the surface area and cross-sectional area. So, as an example, I thought I would look at a cylinder,
and in 20 seconds, I might
find the tension in the support cable and the magnitude of the force applied on the lower end of the
let's compare the surface area with the cross-sectional area. So first of all, if I look at the surface
The
area,
wrecking ball is the load that is attached to the cable.
it actually has three surfaces.
there may be bursts of lifting
So what I'm going to do is
The support cable
add the area of all three surfaces together. There are two ends, and then there's the curved part. So the area of each end is going to be pi r squared, which is the area of a circle. Then I need to add to that the area of the curved part. The way you can think of that is to think of the circumference of a circle, and then stretching that circumference down the length of the cylinder. So the circumference of a circle is 2 pi r. You multiply that by the length of the cylinder. Now what I want to do is simplify this as much as possible. I'll give the surface area the symbol A. I add the two areas of the ends together, that's 2 pi r squared.
The wrecking ball has a weight, W sub L.
And then, to make this easiest to use, I'm going to factor all the common terms out.
Here, the second
So, here's the final term. 2 times pi
The
times
boom weight
radius,
is given as
and
3600
what's left is the
directed
radius
downward.
plus the length.
Later for the city.
So that would be the area
Two
of
angles are
the
also
surface of the
given.
cylinder.
The boom has been
That
raised
area
to an angle of
is
48 degrees above the
boundary
center of excess.
between the object and
We'll
the
give this
cylinder
the symbol
and the
L.
environment. Now if I take that
The second
cylinder
angle
and
is the
slice
direction of
through
the
it,
support cable.
then
This angle is labeled
I would be
theta
measuring
and
the
has a value
cross-sectional
of
area.
32 degrees.
So imagine that this is
We have two unknown variables
the
defined.
applying a
The tension in the support cable
making a
T
block.
and the magnitude of the force.
And I take a knife
Let's say
and I
I'm
cut
pulling
through
on
it.
the block with a
Let's say I
certain
cut through it this way.
force at a
Chop right down through the middle. And when I do that,
For
I
this
get
example, you'll assume that the boom is in
smaller cylinders.
pull the block
Equilibrium has two requirements. The vector sum
So the
of
cross-sectional area would be the new areas that's exposed.
this means the sum
Now
of
really,
the
in this case, there are two of those. I'm not going to double count them. I'm just going to count them once.
I could do better.
So the cross-sectional area,
Like
if
that,
I slice it
displacement, but I'm going to stick
perpendicular
with
to
my
the
begin
length,
with the requirement for the first
then that cross-sectional area is
Here is a
just the
simple
area of a
calculation
circle.
of this
And again, I'm not going to double
This is
count.
the
determine the
compound
force
that
component.
actually
You
count
have to
lower
have
circles, just
information
one of
about
them.
that.
The cross-sectional area would be pi r squared. You can see that's different than the
my
surface
force
area.
component.
In the drawing,
So I
we
use the symbol for
use
that.
the belief
Unfortunately,
that if two
a lot of times
parallel
we use the
lines
same symbol,
travel
A,
in
for area. So you have to know from the context what the symbol is standing for, surface area or cross-sectional. Now what would happen if we took
We
the
have
same
also
Negative
shown
force.
that the angle between the boom and the tension force is equal to
distance
5
instead of,
times
changing.
theta.
We've got the package
cutting
all
it
the way
over
over
here
here
to
at
the
17
length.
millimeters. And now we're going to
So when I
move
cut
it
it
across the
to
middle like
the
that.
other
The sum of
side
the
of the
horizontal
zero
force
mark.
components
stuff
is
down.
shown here.
So
The
if you
horizontal
cut through it like
component
that,
of
let's
the
say
force on the
exactly
hinge
through the middle.
minus the horizontal
What
component
you
of the
would get
tension
the
force.
surface that would be exposed.
Let's solve this
If I
equation
look
for
at it
this.
from the top,
In this
would be a
equation,
rectangle.
we know the value
We're
of
going to use the
theta,
same
but the magnitude of the tension
It's
is
going to
the
be
parameter to
work
be
is
found
equal
for
to
part A.
work done by the spring is going to be equal to
Similarly, we
so
find
the
the sum of the
cross-sectional area
forces in
depends
the
on how
y
you
direction.
slice
I
it,
squared.
which
The
way
component
you
V is
cut
the
the
only
object.
one directed upwards,
So in
while
this
the
case,
two weights,
We're going to
like
put
a
the numbers in.
vertical
The
and
initial
the
position of this
tension
time
arms
Look,
are directed downward.
that's
17
just
is
a
why we're
long
going
way
to
of writing out a dot
We solve
product.
this equation for
and
V.
then
The dot
on
product
the side,
is
that's the diameter of
In
the
equation
circle, which
2,
is the same
we know the
as
value
force
of
vector
the
dotted
and the
to
angle
the
theta.
velocity vector
But again,
r
the
So in this
magnitude
case,
of the tension
cut
force
it
is
here
unknown.
because
in
we're
this
squaring that
direction.
coordinate.
on a dot product.
The
The
cross-sectional
components V
area
and H
Positive
can be used to find the
This
magnitude
is
of
another
the
way
force
that I
F sub
would
P
write
by
down
using equation 3.
being
if I wanted to
sour, if I
express that
happen
in
to
terms
know
of radius,
At this point, we have
the
three
diameter
arguments,
is
done, and this
but
time
only
work
two
is
equations.
positive.
A third equation
me
is
give
the
you a
the
formula.
cross-sectional area would be
It is
2 times the
the
radius
equation for the
times the
sum of
length.
equations.
Package
This will
out.
be
So
addressed
it's
in
important to
part
recognize
two.
the difference between
The spring did
surface
negative
area and
work.
cross-sectional
We
area.
did
This will become
positive
very
work.
important later
There's
on
the
when we
F vector.
start
Here
talking
is a
about
hint on how to
is
find the
how
magnitude of
positive
potential
energy
T
moves from one
and the
place to
force
another
of
because of
gravity
temperature
S
will
difference.
be-
the package
I will
out
have the
from
most
kind of
To
energy
write the
called
torque
heat.
equation, it is helpful to put
Did
the
a
indication
fairly
axis
decent
to
angle on
path
this
In
of
various
expression
cases, will
here
depend on
is now going to be
This will result in a
small
sum of
amount
torques
negative
equation that will
work.
So
enable
it's a
you
good
to
idea to
solve for T
distinguish
in terms of the known
sine
variables.
of 0, which
Be
is
sure to find the
12.
correct
And I've
lever
recommended
arm
to go
for
through the
each
same
force
procedure
acting
for
on
other
the
Large
shapes.
amount of positive
what do
work.
I get if
spheres.
I
After
Negative
finding
work.
T,
You
use
at
its
an
value
angle
in
of
equations
like
1
that.
and 2.
9 degrees.
Then
Once
we'll
you
be
have the
moving
components
on.
of F sub
sliding.
T,
See
So go
how
ahead
you
and
can
try
then
that out.
complete the solution.
And now
And we'll
I'm
see
pulling
you later
upward,
on.
not enough to lift the block. It's still sliding across the floor. Can you see that this is, shall we coin a phrase, stupid? Because if I put in 90 degrees right there, cosine of 90 is 0. I'm pulling up for nothing. The power that I'm using to move the block is 0. I may be straining muscles, but I'm not going to be making the block go faster or slower. Now, for 0 degrees, I had the most power I could get with the given amount of force, and so I would be making the block go faster and faster and faster. I'm adding energy to the block. I'm adding nothing, no energy to the block here. And one more case, block's still sliding to the right, but I'm pulling to the left. So the angle between the displacement vector, still x to the right, and the F vector, well, that's going to be 180 degrees. Can you see that when I put this in, I get -1? I will be removing energy from the block. I'll be making it go slower and slower. The power that I'm applying to the block is now a negative number because I'm taking energy away. Let's do a little quick summary of ideas here. Power is the ratio of work to time. Average power, you're averaging the amount of work being done over a time interval, 30 seconds, an hour, a day, something like that. But you could be worried about the power at a given instant, instantaneous power. That's the rate at which work is being done just then. We can also write power, the instantaneous power, as the dot product of the applied force and the velocity of the object just then. And this is the way we can expand the dot product, magnitude of F, magnitude of V, cosine of the angle between those two vectors and the dot product. And that's it for this little video.